I'll just make up a hypothesis test question, kind of go through it from start to finish. Got my camera a little bit out, I think. Should that be down? That should be up then. Okay, we are good. So let's suppose that we were trying to see, compare two things. And we're talking about comparing the means of two populations. So while I'm thinking about it, we'll have population one. And population one is going to be I need a topic. For no other reason except it's a stupid thing to measure, I've decided that we're going to compare Americans the length of the right hand index finger. So you get your finger and they measured it, and we compared that against population two. And population two is going to be Scotland. And we measured the length of their index finger. And so we're interested in, are the average index finger, right? So we have an evidence then. Is there evidence to prove that the right indexed finger of Americans is greater than the right index finger of Scottish people? So this is the quest of this experiment. Can we get evidence to prove that American's finger is longer than a Scotsman's? So you collect sample. You collect 200 random Americans, and you find out that the mean length of their index finger is, look at my finger as a judgment, is 4.7 inches, and that the standard deviation is 0.3 inches. And you collect the same information from the second population. Let's say it's 150 of them. And this thing is 4.4 inches. And the standard deviation is 0.4 inches. We are going to test, is there evidence to prove that Americans' fingers are longer than Scots people? And we are going to do it to a significance level of 0.05. So that's what we're trying to prove. This is the evidence that we've got right now. So the way the hypothesis test works is that you have a kind of procedure that you go through. So the first thing you're going to do is you're going to do the null and the alternate hypothesis. You're going to state that formally. Well, in this case, the population of Americans, which is mu1, take away the population mean of the Scotsman, which is u2, is 0. That is always going to be your null hypothesis, right? And then the alternate depends on what we are trying to prove. Now, we are trying to prove that Americans is bigger than that. And so when you're trying to prove that the first thing is bigger than the second thing, you do mu1, the population mean of Americans, take away the population mean of Scotsmen is greater than 0. Because when that's greater than 0, mathematically that's the equivalent of mu1 being bigger than mu2. That's how you state it. once we go there, we essentially, the next phase is calculations. We are going to find the standard error of x1 bar take away x2 bar, which is the square root of that guy over that guy. In this case, the calculation is going to be, here we go, 0.3 over 200, so 0.3 squared over 200, plus 0.4 squared over 150. Then you come here and you do your calculator. If you were doing this question in the final exam, you would probably get like an A, B, C thing, and A would be state the null and alternate hypothesis, and you write that down. And then B would be find the standard error. So I would try and help you by asking you to find things I know you need to find. So you do this bit, and let's see what it comes to. 0.3 squared divided by 200. Add 0.4 squared divided by 150. And we'll get to 3 decimal places, 0.039. So the next stage would maybe ask you for the standard error. You'd also get, what's we got here? You also get what's called the t-score. And the t-score is given by this formula. And when it's means, it's always a t-score. And when it's proportions, it's always a z-score, right? And you put these guys, and this calculation comes out to be 4.7 subtract 4.4 divided by 0.039. So I'll do 4.7, take away 4.4, hit enter, divide that by 0.039, and I will get t-score of 0.3692 to 3 decimal places. Are we comfortable with so far so good, right? Null alternate hypothesis depends on the story. Do you want the first thing bigger than the second? Do you want the first thing less than the second? Or do you just want to prove that they're different? Well, that's 3 choices. The next stage is we're going to get a p-value. That has to be done in SALT. And that's going to be the probability that you get a t-score. Now it's either going to be greater than this number, less than this number, or just essentially not equal to this number. Now you can tell which of the 3 it's going to be by looking here. That's a greater than, this is the same. And at this point, you need SALT. And so what would happen if this was done in the PDF version? You would do all of this working, and then you just go to a special question I'd set up that essentially had a SALT button on it, and you just use that SALT button. So I'm going in right now. And let me just show you what it would look like. Just closing off all these annoying windows that they have. Okay. So what I would do then, it would say, you know, use SALT to find the p-value, which is what I'm doing. You hit the SALT button. Right, first thing you have to decide is, where do you get the p-value? Is it in distributions? Or is it in inferential statistics? Where is the right place to look?
Distribution.
Okay, so if we went to distribution, there's nothing here that does it? Well, if it's not in the one place, it has to be in the other. And the reason I know it's in this one, isn't this the only one that has a 2-sample T? So if you go in the wrong place, you'll find out it's the wrong place because you can't find the guy you're looking for, right? You know you're looking for a 2-1, so we click on it. And essentially we put all the numbers that we want here. And so the first one is going to be 4.7. This is the Americans. The second number is going to be 0.3. And the sample size in this case is 200. And then the second one, the sample mean, is 4.4. The standard deviation is 0.4. And the sample size here is 150. And it's set up to have hypothesis test. You leave this as 0. And we were wanting the greater than 1, weren't we? And I'm not going to make any assumptions of equivariance, so that's what I typically do. If I did want you to do that box, I would try and make it much clearer. I would say, you know, pull the data or assume that they're equivariance. Now, can you see our T statistic? Oh, did I get my numbers right? 4.7, yeah, 0.3, 4.4, nothing, 0.3. My T statistic is a little, oh no, it's not. 7.703 and I got 7.692. Do you know that was just caused by rounding? They don't do any rounding. They do all their calculations to whatever it is, 6 decimal places. So I'm cool. I thought for a minute I got it wrong, but I wasn't. And there's your p-value. Isn't that essentially them telling you that the answer is practically 0, isn't it? It's definitely less than a whole lot of nothings. So 0 would be my answer. And now we should be able to. I've lost my window. Where's my window? Oh, here it is. Good. So what we then do is return back here, put in 0. And the last part of this puzzle, well, this basically 2 parts, but this part is we now test. And our test is our p-value that we just got less than the significance level alpha? In this case is 0, less than 0.05. And if the answer, as it is here, is yes, we have a conclusion then. And you can write this conclusion in a number of equivalent ways. The way I would probably write the conclusion is, there is enough evidence to accept the alternate hypothesis. That's kind of the formal way of saying it. You can also write it down by saying there is enough evidence to reject the null hypothesis. And a third way would be much more like English. There is enough evidence to prove American finger are on average longer, than Scots people's fingers, which is essentially what we proved there, didn't we? Now, that was a silly, just off the top of my head thing, but you can use this process to scientifically prove, and it will be accepted in the science community, that you have proved what you said you proved. So here I'm just pretending I proved American fingers are longer than others, but couldn't you also equally use this to prove that one type of material was stronger than another? Suppose you were working for a company and you were into, buying parts and you wanted to test them, right? You do destructive testing, right? What was the average number of miles before, the shock absorbers broke, right? What was the greatest amount of weight they would take, before they snapped? What was, whatever. What was the greatest amount of air pressure you put in the tire before it burst? Now, you don't just do it to one tire, right? If Ford are buying tires, they probably buy 100 of them, right? And they destructively test them, right? They blow them up more than they should ever be blown up, right? And they record what, PSI they blow up at. And that would be one way for them to say, this tires that we're getting out of Korea and this tires that we're getting out of China, the tires out of Korea, are stronger, right? They take more pressure on average before they explode, whatever it might be. But this is not subjective, right? You set up this thing and you do it. You do it in pharmaceuticals. You do it everywhere in science. This is the bread and butter of how you prove things in science. So it's a biggie. Okay. Any questions about what happened in this one? No? Okay. So someone else can have a shot then. What's the next topic, question, or whatever you want me to go over?
I guess mine kind of has to do with the hypothesis testing as well. When do we use the was it the standard deviation over the square root of the sample size rather than the square root of the, like we just did?
Right. So you're doing a standard error of one sample, a single population one. Then you're going to do, well, actually the formula doesn't even look like that. You're going to do a formula that looks like this. So that would be in a story where, for some reason, you actually know what the population value used to be, right? So you get a story where the population average mu used to be 20, right? And now you think it's different. So that would be when there's only one sample. Right, so if you're doing a story where, in the past, the number of cigarettes, the average number of cigarettes an American smoked is 20, right? Because some of you smoke none and some of you smoke 60, right? And that was in the past. But now you think it's less, right? So you know that as a fact. You think it's less and you go into one sample, right? You find 500 Americans and find out the average number of cigarettes they smoke. That is a one sample situation. That's what the standard error looks like. In that world, in that story, your null hypothesis and then your alternate are different. Because there's only one population, you have mu equals 20 to represent what it used to be. And mu is now less than 20 because you think it's different, right? It's changed. And when you've only got one population, that's what the null looks like, right? That's what the alternate might look like. The standard error will look like this. And there's only going to be one sample, so they've no numbers, right? S is the standard deviation of that sample, and this is the square root of n. And your t-score, because there is going to be one, is going to be a little bit different as well. It's going to be the mean take away mu naught over the standard error x bar. What number is this mu naught?
20.
Yeah. So do you see the formula for the standard error is a little bit different? the formula for the t-score is almost the same, but it's got a little bit of difference in it as well, doesn't it? Compared to the one we just did.
Yeah, that helps clarify it a lot. Thank you.
Yeah. The rest of it is identical, right? You get the p scored the same way, right? In terms of a t-score. Conclusion is the same, the test is the same, right? So a lot of similarities, but this is the main difference. Okay, what's the next one? As I say, yeah.
What equations do you think are like some of those important to know for the final?
Every single equation is important to know. I'm not giving you any clues, sorry.
All right.
So you're going to, you know that the hypothesis testing has taken us 3 weeks. So you know you're going to get a fair chunk. That's 30% of what we've done, right? So don't be surprised if you get 3 questions, right? 3 out of 10 is 30%, maybe even 4 in the final. That's just seems reasonable assumption. So you're going to have to know all those standard error formulas for proportions and means, things like that. A lot of the same formulas, don't they get used in confidence intervals as well? I mean, so there's a big overlap. So the same kind of formulas get used in different places. Okay, what's the next question?
Hypothesis testing with proportions instead of means.
Okay, which a single or a 2 population world? Sorry.
Either, really.
Okay, we'll do a 2 because they're, I think, a little bit harder. So this is going to be hypothesis testing. For the difference in 2 proportions. Okay, let's do a pretty classic one, which is a clinical trial. This would be a reasonable story. So in this case, we're going to have the new drug, and we're going to have the old drug. And the proportion that we're going to be finding in both of these groups is the percentage of successes, right? So success could be, it depends on what the drug does, but success could simply be that they're still alive, right? It saved their life. So let's say it's that. So we've got a new drug therapy, and we want to compare it against the old drug therapy. And we think that the new drug does a better job than the old one, right? So we think that this proportion is bigger than that one. So this is going to be number 1, and this is number 2. While we're at this, as we're doing these things, this is called the control group. And this is called the experimental group. So what do we do? Well, if we want to prove that the new drug is better than the old, we have to collect evidence. And so we collect a sample in a clinical trial of 200. Well, it wouldn't actually be 200 volunteers. It might be 500 volunteers who are evenly split amongst the 2 groups. And when you try and make it a double blind, by a placebo, the whole 9 yards, if it's possible. So 200 get the new drug, and the success rate was 170. P2, the other drug, we get a number that's reasonably close to that one. 170. 248. Now, P1 and P2 are always going to be proportions, right? Decimals less than 1. And so don't put 170 in and don't put 248 in. You know, like when the means, the numbers 82 and 90, right? When you do means, the numbers are big, right? They could be 400 and so on, but in proportions or not. So in this case, oops, this fella here is 0. I think it's 85. Yeah. And over here, 240. Try that again. 248 divided by 300, and that's about 0.827. That says 827.87. Right. We also need a significance level. And let's say that since this is people's lives and drugs, you would want to use the smallest significance level you could find, which in this case I'm saying is 0.01. Which basically means if I do manage to prove that this drug is better than that, isn't this how many times I would get that wrong? In other words, I could say it, but there's a 1% chance that it was just randomness that gave me this information. It wasn't really the first drug is better than the second, which is all you can do. You can't really do more. So that's the information. It's going to be set up, as all hypothesis tests are, in a very similar way to each other. Now, the way you write the information is a little bit different. You call them P1 and P2 equals 0. And that's the null hypothesis in every situation. When it's two proportions being compared, that's the case. Now, in this one, the alternate depends on what you're trying to find evidence for. The way I've phrased this story, aren't I trying to prove that this is bigger than that? So P1 take away P2 greater than 0, less than 0, or not equal to 0.
Greater than 0.
Does that make sense, guys? So once that is done, we then have to essentially calculate the standard error. And the standard error depends on, what you're finding. In this case, it's proportions. So it's the standard error for the difference in two proportions. And it has, at least the version we're going to use is the unpulled one. Which is that guy. So I'm now going to go and do the square root of, I should put the numbers in, shouldn't I? This is P1 hat, so it's going to be 0.85 or 0.15 over a sample size of 200 plus 0.827, 0.173 all over 300. So here goes 0.85 times 0.15 divided by 200. I'm going to add 0.827 times 0.173 all divided by 300. Boom. And the answer we get is 0.033 approximately. Now, since this is a proportion, what they call the test statistic, call it the z-score, is going to be this formula. P1 hat take away P2 hat over the standard error. So that's going to be 0.85, take away 0.827, divided by 0.033. So 0.85, take away 0.827, divided by 0.033. I get the number 0.697. So far, so good. Next thing we're going to do is get the p-value, calculate it. And the p-value is the probability that you get a z-score. It's either bigger than that number, less than that number, or not equal to that number, right?
Bigger.
It's greater than again, right? And at this point, we're going to have to use salt. So me take us over to salt. Okay, well, I'm to my window. So I'll take you over to salt, and I'm just going to use that button. Boom. Right, we have the same kind of place. Where's this little guy hiding? Well, if you go to distribution calculations, you can get the normal distribution. And the mean is 0 and the standard deviation is 1 because it's always those for a z-score. And we are looking for a greater than, so that's right-tailed. And we want the number here to be 0.697. And the p-value is 0.2429. Are we okay with that? So let's move on. Can basically complete this question. So now we do our test. And our test is the p-value that we just found, is it less than significance level alpha? In this case, it's 2429. And is it less than 0.01? In this case, it's clearly a big fat no, right? It's not. And when that happens, you have your conclusion. And the typical way you would write down a conclusion, well, the lawyer version would be, there is not enough evidence to reject Angel. That's really the only version of the null, that conclusion. In English, you might say, there is not enough evidence to prove the new drug is better than the old. Now, that statement, this one here, it's equivalent to what's up there. But I'll tell you what it doesn't mean. Some people think it means more than it does. That really is quite a weak statement. All we're saying is, look, there's not enough evidence to prove that the new drug is better than the old. Now, that doesn't mean that the old drug is better than the new, right? We haven't proved that. We haven't proved that they're equally good. We haven't even proved that one is worse than the other, right? All we've been able to say is we don't know. That's the bottom line. That's all you've actually proved. And that's pretty weak, right? It's a bit like saying, well, I've just spent 5 million on a clinical trial and maybe another 10 million in research and development. And the only thing I get out of it is that we don't know if the new drug's any good. It may be better, may not. Well, hard luck. That's life, right? Find a better drug. The FDA is very, very strict about how you prove a new drug works. And they're essentially going to be done through clinical trials as we've done here. In the usual run of things.